GCE Advanced Level Chemistry Practical Series Experiment number 2, displaying the shapes of molecules and ions using a molecular modeling kit. The aim of this experiment is to provide understanding on different types of bonding that we see between atoms and orientation of atoms in the three-dimensional space for simple molecules and ions. So in simple terms, students, we are going to be using a molecular modeling kit to show how each different atom of a given molecule is distributed in the three-dimensional space. When you're drawing or when you're writing down the structure of a given molecule, you will always have to draw it on a piece of paper. Sometimes we use 3D images, but we are going to be visualizing, or we are going to very clearly see today in this experiment how each of these atoms of a given molecule is distributed in the three-dimensional space, so that you can remember how atoms of different molecules are distributed in a three-dimensional space, or whenever you are coming across these molecules in the future, it will be easier for you to visualize how atoms of different given molecules are distributed in a three-dimensional space. So let's move on to identifying the equipment we will be using for this experiment. Now students, let's identify our equipment that we'll be using for this experiment. For this experiment, we are going to only be using a molecular modeling kit, and this kit usually comes with a variety of different balls and connectors such as these. These are also known as linkers. So each of these balls that we have over here will represent atoms. Each of these balls will represent atoms, and we are going to be using these connectors to represent bonds. For example, by connecting two balls like this with a single connector, we have now indicated a single bond between two atoms. These connectors are flexible. So when you want to indicate a double bond, we will connect another linker to one of the atoms, and we can bend these linkers and connect the two atoms like so. And now what you see here is two atoms connected to one another with the use of two bonds. So basically, this can be used to denote a double bond. So students, this is how we will be using the molecular modeling kit. And when talking about the molecular modeling kit, we have a color coding that we usually use, which is referred to as the CPK. There are a variety of different atoms or different balls that are going to be coming from different colors. And these different colors are there due to a color coding system called CPK coding system. So CPK stands for Curie, Pauling and Colton, who are the scientists that actually came up with this molecular modeling system. So CPK are the initials of the developers of this molecular modeling system. And according to the CPK color coding system, the black color balls are used to represent carbon atoms. And as carbon has a valency of 4 and can form 4 bonds, These black color balls usually have 4 holes in them. 1, 2, 3, and 4. There will be exactly 4 holes in these black color balls that are usually used to represent carbon atoms. In certain modeling systems, even gray color balls are used to represent carbon atoms. White color balls are used to represent hydrogen atoms. And as hydrogen atoms can only form one bond, you can see this white color ball has only one hole in it that can connect to one linker or one connector, indicating that these atoms can form only one bond. We have red color balls, which are usually used to represent oxygen atoms, and oxygen atoms most of the time end up forming 2 bonds. Oxygen has a valency of 2. So therefore, you can see these oxygen atoms or these red color balls have 2 holes in them. So red color balls are used to represent oxygen atoms. Apart from that, we use blue color balls to represent nitrogen atoms. Most blue color balls will have 3 holes to represent the 3 bonds nitrogen atoms form majority of the time. And nitrogen atoms usually have a valency of 3. So therefore, most of the blue balls that you come across in a molecular modeling system will have 3 holes in them. At certain times, when nitrogen forms ions like ammonium ions, you will see nitrogen forming 4 bonds. So you will come across certain blue color balls that has 4 holes in them. Apart from that, we use yellow color balls to represent sulfur, and green color balls to represent chlorine. However, in this practical, when we are carrying out this practical, we will be mainly looking into choosing a correct central atom with the correct number of holes in it to represent the correct number of bonding that it forms. So we might, depending on the molecule that we are dealing with, we might deviate from this CPK color coding system, because we are mainly interested in constructing molecules with the correct shape and the correct number of bonds. So when we are trying to construct molecules with the correct shape, we need to choose a central atom with the right number of holes in it. So therefore, we'll be using a central atom with the right number of holes first, and then we'll be moving on to constructing the molecule. So without further ado, let's move on to constructing our first molecule. Students, to develop an idea about the shapes of different molecules, or how each atom of a given molecule is distributed in 3D space, we can use a theory that is known as VSEPR theory. I'm sure you have already learnt about this. VSEPR stands for valence shell electron pair repulsion theory. So according to this VSEPR theory, we learn that when it comes to a central atom of a molecule, the electron pairs around the central atom are usually arranged in such a way that it minimizes the repulsion between electron pairs. As you know, electrons carry a negative charge, and we know similar charges will repel one another. So if you take a central atom, and if around the central atom, if we have few different electron pairs, these electron pairs will be arranged around the central atom in such a way that it minimizes the repulsion between these electron pairs. In order to minimize the repulsion between these electron pairs, they have to be spread as much as possible away from one another. So, VSEPR theory shows us how, or it communicates to us how electron pairs around a central atom are distributed around the central atom. So, in this case, we learn that they are distributed in such a way that maximizes the distance between two electron pairs to minimize the repulsion between them. Usually, students, there are two main types of electron pairs. One type is the bonding electron pairs. Usually, when two atoms bond together, we know that when a covalent bonding is formed, electrons from each atom is shared to form this bond. So, when two atoms get together to form a bond, when they share electrons, there's going to be a shared pair of electrons between the two atoms. Or in other words, between two atoms, there will be a shared pair of electrons. Or in other words, between two nuclei, there's going to be our shared pair or shared pairs of electrons. So a covalent bond is essentially the electrostatic attraction that is existent between the shared pair of electrons and the two nuclei of the atoms that are going to be forming the covalent bond. So a covalent bond is formed when the two nuclei is trying to attract the same shared electrons. So these shared electrons are caught between these two positively charged nuclei. So therefore, the bond electrons are limited in its movement. So one type of electron pairs that we find is bonding electrons, and we learned bonding electrons exist between two nuclei. So therefore, they are getting attracted to both of these nuclei. Because of that, their movement is going to be limited. And then we have lone pairs of electrons. Lone pairs of electrons are the type of electrons that do not take part in forming a bond. However, these electrons are found in the valence shell or the outermost shell of an atom. So therefore, they also contribute to the shape of the molecule. So these lone pairs of electrons, they are not present between two nuclei. They are only attracted to one nuclei because they do not form a bond. Therefore, they have a more of a spatial distribution, or in other words, they acquire more of a spatial volume. Since they are not present between the two nuclei like bond electrons, these lone pairs of electrons have greater movement, so they acquire a larger spatial volume. So students, we learned about two main types of electron pairs: bond electron pairs and the lone electron pairs. Bond electron pairs will have a smaller spatial volume, or they do not get distributed quite a lot in the three-dimensional space. However, when it comes to lone pairs of electrons, since they are attracted to only one nucleus, they have a greater spatial distribution, meaning they acquire a greater spatial volume, or they are spread throughout a greater area. So after identifying this, we are going to be using our VSEPR theory knowledge to realize how each of these bond electron pairs and lone pairs are going to be distributed in the 3D space. Now, keep in mind, students, when it comes to a single bond is going to be considered a singular repulsive unit. Lone pair will also be considered a singular repulsive unit. However, multiple bonds, that means if you take two atoms and if the two atoms contain more than one bond, such as double bonds or triple bonds, these type of multiple bonds are going to be considered as a singular repulsive unit. Although there are two bonding electron pairs, if we are talking about a multiple bond like double bond or triple bond, we consider them to be a singular repulsive unit. So, based on the repulsive units around a given atom, we have different shapes formed around a given atom. To simply put how different shapes are formed, let's take a look at few examples. If you take an atom where there are only two repulsive units, if you take a central atom where there are only two repulsive units, then we need to arrange these two repulsive units in such a manner that minimizes the repulsion between them. At that point, the best way to keep these repulsive units the furthest away from one another is to keep them opposite to one another, meaning create a 180-degree bond angle. And when we take a look at a central atom with three repulsive units, they will be kept away from one another with the use of a shape known as trigonal planar. Now, we will be demonstrating all of these shapes with the molecular modeling kit we have over here. So, at that point I will explain this further. But just before we start, we need to be clear about the different shapes that are there. So, when there are three repulsive units only without any lone pairs, we have trigonal planar shape. When you only have four repulsive units, the electron pair geometry would be tetrahedral. When you have five electron pairs around a central atom, the electron pair geometry would be trigonal bipyramidal. When you have six, it's going to be octahedral. So, while keeping these shapes in mind, we can now move on to constructing the shape of the first molecule that we have here, which is ozone. Now, to make life easier for you all and to make it easier for you all to understand what we are going to be talking about, I have drawn the Lewis structure of ozone here. You can see we have a central oxygen atom double bonded to another oxygen atom, and we have oxygen-oxygen single bond that you can see over here, and the single bonded oxygen atom has a negative charge on it because there is an additional electron there around this oxygen, and around the central oxygen atom there is one electron missing, so there is a positive charge, and the overall charge of the ozone molecule is going to be neutral. Now, let's take a look at how we deduce the shape of this ozone molecule. In order to do that, we need to take a look at this table. We need to first find out the total number of electrons or total number of electron pairs in the valence shell around the central atom. To deduce the shape of the ozone molecule, you have to first take a look at the total number of electron pairs. The total number of electron pairs in the valence shell around the central atom. So, we have our central atom here. Around the central atom, how many electron pairs are observed? As you can see over here, due to this double bond, there are two bonding electron pairs, and this single bond brings in another electron pair. So, there are three bond electron pairs and 1 lone pair. Altogether, we have 4 electron pairs around the central atom of ozone. And according to our VSEPR theory, the repulsion units that we have around the central atom of ozone is going to be 3. Now take a look at this. According to our VSEPR theory, we learn that lone pairs act as 1 repulsive unit, single bonds act as 1 repulsive unit, and double bonds or triple bonds act as 1 repulsive unit. Just because it is a double bond, we don't consider it to be 2 repulsive units. We consider it to be 1 repulsive unit. So over here, how many repulsive units do you see? We have 1, 2, and this double bond is going to be our 3rd repulsive unit. So around ozone's central atom oxygen, we see 3 repulsive units. And one of them is going to be our lone pair. How many lone pairs are present on ozone? Or how many lone pairs are present on the central atom of ozone? 1. So while keeping that in mind, we can now move on to electron pair geometry. The word electron pair geometry refers to how these electron pairs are distributed around the central atom. There are 3 electron pairs around the central atom. Or we can say there are 3 repulsive units. The correct way of communicating it would be there are 3 repulsive units, because we consider the double bond to be a singular repulsive unit. So around the central atom of ozone, there are 3 repulsive units. And how do we arrange 3 repulsive units around a central atom to minimize the repulsion between those 3 units? By arranging these repulsive units in a trigonal planar arrangement. And therefore, the electron pair geometry of ozone is going to be trigonal planar. However, when you are taking a look at the molecule will have a shape called the angular shape. This is because when you are observing the shape of the molecule, the lone pair will not be visible, only the bond electron pairs will be demonstrated using our molecular modeling kit over here. So you can very clearly see the shape of the molecule is bent or angular. So this is why we will be seeing an angular shape when it comes to our ozone molecule. So let's construct this molecule and observe the shape of the ozone molecule being angular. Now, in order to demonstrate the shape of the ozone molecule, we need to choose 3 of the same type of ball that we can find over here. Usually, oxygen is represented with the use of a red color ball, but currently we have red color balls in this particular modeling kit with only 2 holes in it. So therefore, we will be using a black color ball instead, because we have the relevant number of holes to show this shape using a black color ball. So oxygen in this case will be represented by 3 black color balls, and we'll be using these linkers as bonds. So we can see, first of all, there is 1 oxygen connected to the other oxygen atom with a single bond. So we can connect the single bond like so. And then we have the second oxygen connected to the central oxygen atom with a double bond. So we are going to use two linkers to connect the second oxygen atom to the central atom. So now students, if you observe over here, you can see we have the first oxygen atom or the central oxygen atom. Central oxygen atom over here connected to one oxygen atom through a double bond, and it is connected to another oxygen atom through a single bond. We know that the lone pair is not going to be visible when you're talking about the shapes of the molecule, but usually if a lone pair was present, it is going to be present over here. However, since the lone pair is not going to be visualized, we'll be removing this linker, and now we can see the bent shape of the ozone molecule. Now we'll keep it here for the time being. Students, when it comes to the repulsion between electron pairs, there are three main types of repulsions. We know that there are two main types of electron pairs, but there are three main types of repulsions. First one, and the most weakest type of repulsion, would be the repulsion that exists between bond electron pairs and bond electron pairs. So bond electron pair repulsion is somewhat weaker. And then we have moderately strong type of repulsion that exists between bond electron pairs and lone pairs. As I mentioned earlier, lone pairs have a greater spatial distribution, so the electron clouds are distributed further into the three-dimensional space, exerting a greater repulsion on bond electron pairs. So bond electron pairs and lone pair repulsion is going to be greater than bond electron pair repulsion. Finally, the greatest repulsion is observed between two lone pairs. So lone pair repulsion is the greatest repulsion that you see in a molecule, and then we have lone pair bond pair repulsion, and the smallest or the weakest type of repulsion that you observe is going to be bond pair repulsion. So comparatively, the weakest repulsion is bond pair repulsion. Comparatively, the greatest repulsion that you see within a molecule is observed between lone pair repulsions. So over here, the electron pair geometry of this molecule, ozone molecule, is trigonal pyramidal. The electron pair geometry is trigonal pyramidal. However, the shape is angular. When you have a trigonal pyramidal electron pair geometry, the bond angle or angle between the electron pairs is usually 120 degrees. However, you can see you do not have a bond electron pair here. Instead, we have a lone pair. The lone pair is distributed in a larger spatial volume, exerting a greater force of repulsion between, or exerting a greater force of repulsion to these two bonds. So therefore, their bonds get or come closer together for a shorter or smaller bond angle here. They will not have 120 degree bond angle here. Instead, due to the greater force of repulsion that is exerted from the lone pair of electrons that would usually exist around here, these two bonds will come a bit closer together and will create a smaller bond angle less than 120 degrees. Usually it is going to be 120 degrees when you have the trigonal planar electron pair geometry. However, the shape of this molecule is bent, indicating that there's a lone pair of electrons here. This lone pair of electrons will exert a greater repulsion to these two bond electrons. So therefore, the bonds will come closer together to have a smaller bond angle than 120. So over here, the bond angle is not 120. It is going to be smaller than 120. Something that you should be keeping in mind, students. When there is a lone pair of electrons, it will make the bonds repel more and will make the bond angle smaller. So that is the shape of the ozone molecule, and we learned about the bond angle of the ozone molecule as well. Bond angle of the ozone molecule is not 120. It is slightly smaller than 120 due to the presence of the lone pair. We learned that the lone pair exerts a greater repulsion on the two repulsive units consisting of bonding electrons, and will make the bond angle smaller than 120 degrees. So we can see here, when it comes to the electron pair geometry of ozone, it is going to be trigonal planar because we have three repulsive units here. However, one of the repulsive units is a lone pair. You cannot visualize the lone pair, so therefore the shape of the molecule is going to be observed as an angular shape, and the bond angle is going to be smaller than 120 degrees. Students, let's take a look at beryllium chloride, or BeCl2. Now, as you can see, when it comes to beryllium chloride, we can very clearly see beryllium is the central atom, and we have two chlorine atoms on either side of the central atom. So the Lewis structure of beryllium chloride is given here. And if you analyze the electron pairs around the beryllium atom, you would notice that beryllium atom has two bonding electron pairs in it. Around the beryllium atom, you only will find two bonding electron pairs, and beryllium doesn't have any lone pairs in this particular instance. So let's take a look at the total number of electron pairs in valence shell of the central atom. That is going to be exactly 2. And the number of repulsive units is going to be exactly 2. So the repulsive unit number when it comes to the central atom beryllium is going to be 2. And number of lone pairs in the central atom is 0. So the number of repulsive units and the number of electron pairs around the central atom at this point are equal to one another. So you won't have two different electron pair geometry and a molecular shape. The molecular shape and the electron pair geometry will be the same since we do not have any lone pairs. When we have lone pairs, the electron pair geometry and the shape of the molecule is going to be different. So in this case, electron pair geometry is linear and the shape of the molecule also happens to be linear. Meaning, around the central atom beryllium, you are going to have two chlorine atoms directly opposite one another. Why is this? Because the central atom has only two repulsive units, and according to VSEPR theory, we need to make sure that these two repulsive units are separated to the maximum possible distance, and that distance can be obtained when these two repulsive units are directly opposite one another. So to indicate this particular shape, we can use a ball that has two holes that are directly opposite one another. You can see if you take this gray color ball over here, we have a hole that is present over here, and directly opposite to this hole we have another hole over here. Now this particular gray ball has other holes as well, but we chose this gray ball mainly to demonstrate how the two bonds of beryllium is going to be directly opposite one another, forming a 180 degree bond angle. So to indicate the bonds, we will be using these linkers or connectors. So we will connect each of these bonds like so. So this is the beryllium atom represented in this gray color ball here, and through a bond it is going to be connected to a chlorine atom. So to represent the chlorine atom, we are going to take a green color ball. This green color balls are usually used to represent chlorine atoms, and they only will contain one hole. So you can insert or you can fix the chlorine atom to this same bond, and now we have made one chlorine beryllium bond, and directly opposite to that we can connect another bond, and to this also we will be connecting another chlorine atom, forming beryllium chloride. Now this is the molecular shape of beryllium chloride. We can see the chlorine, beryllium, and the second chlorine atom, all three of them are present in a straight line. So therefore this molecule is linear. This molecule is linear. If you want to observe that they are present in a straight line, we can see that all three are present in a straight line, right? So if you angle this, you can see all three are present in a straight line. So students, the shape of this molecule is linear, and the bond angle between chlorine, beryllium, and chlorine atoms is going to be 180 degrees. And the shape that we observe here is known as a linear shape. So when you only have two repulsive units and no lone pairs around a central atom, you are going to be obtaining this linear shape. Now, after observing the shape of beryllium chloride, let's move on to the next molecule. Now, we are going to take a look at the shape of boron trifluoride or BF3. And the Lewis structure of boron trifluoride is given here. Boron is found on the third group of the periodic table, and we can see we have three bonds formed from the central atom boron, and the valency of boron is going to be 3. And after observing the Lewis structure of boron trifluoride, we can move on to this table that we have over here. Let's observe the total number of electron pairs in the valence shell around the central atom. So around this central atom, how many electron pairs can you see? How many electron pairs can you see? We have 3 bonds, meaning 3 bond electron pairs are going to be found around the central atom boron. Do we have any lone pairs? We don't. So therefore, we have a total of 3 electron pairs in the valence shell around the central atom. What about the repulsive units? How many repulsive units do we see around the central atom of boron here? We have only 3 repulsive units. We have 3 bond electrons. We don't have any lone pairs. So therefore, the total number of repulsive units and the total number of electrons around the boron atom is going to be the same, because we don't have any lone pairs of electrons. So since the number of repulsive units and the electrons around the central atom are the same, we can be sure that the electron pair geometry and the shape of the molecule is going to be the same. Like I mentioned earlier, students, electron pair geometry refers to how these different electron pairs, there are 2 different electron pair types, how these 2 types of electron pairs are usually distributed around the central atom. We have lone pairs and bond pairs. In this particular example, we only have bond pairs. So when you have both of these types of electron pairs distributed around a central atom, the shape that it creates with just the electron pairs is referred to as the electron pair geometry, meaning how electron pairs are distributed around the central atom. But if few of those electron pairs are lone pairs, you do not see them in the final shape that we observe of the molecule. So therefore, when we talk about the shape of the molecule, we can't visualize or we can't see the lone pairs. We only will observe the bond electron pairs connecting different atoms together. So therefore, the shape of the molecule will be made only with the use of bond electron pairs. So therefore, the shape of the molecule will be different to the electron pair geometry. However, electron pair geometry decides the final shape of the molecule. So in this case, the electron pairs around the central atom and the number of the repulsive units are the same, meaning no lone pairs are there, which means the electron pair geometry and the shape of the molecule happens to be exactly the same. So to represent this particular molecule, again, we can take this gray color ball that we have here in this modeling kit. So you can see there are only 3 repulsive units. What is the best way to separate 3 repulsive units? The best way to separate 3 repulsive units is by keeping these 3 repulsive units in a single plane at a 120-degree angle, creating a trigonal planar arrangement, which means we need to have each of the bonds separated from one another at a 120-degree bond angle. So that's why we use this particular ball in our modeling kit, because this ball has 3 holes. If you can see over here, 1 over here, 2 and 3. We have 3 balls separated at a 120-degree angle in this particular ball. So we will be using this to demonstrate the shape of boron trifluoride. So we know if this atom represents boron, we need to have a bond connected to the boron atom. Then to represent our fluorine atoms, we can use yellow color balls that we have over here, which has 1 single hole in it. So we'll be connecting these yellow balls to represent fluorine atoms. So we have now created a boron fluorine bond, and we will now rotate this and we will connect another link over here. So boron now shows a new bond here. To this link we can connect another yellow color ball representing a fluorine atom. So now we have made two boron fluorine bonds, and finally we will connect the last bond over here and connect another yellow ball, completing the boron trifluoride shape. You can see we have now made our boron trifluoride shape. You can see the bond angle between fluorine, boron and fluorine is going to be 120 degrees. The bond angle between fluorine, boron and fluorine again is going to be 120 degrees. You can see the same bond angle between each of these bonds. This is the best way to separate three repulsive units to minimize the repulsion between each of these electron pairs. Now imagine if you think, no, there can be a better way and we can fix it somewhere over here. Now the bond angle is somewhat different, so this is a better option. If you think like that, if you observe closely, you can see the bond angle is smaller if you place it in any other place, right? You can see these bonds have come closer together. But if you place it where it originally was, now we can see these electron pairs are very clearly separated with a 120 degree angle, which is the maximum amount of separation you can obtain around a point when there are three repulsive units only. When there are only three repulsive units, the best way to separate them out to minimize the repulsion between these repulsive units is to have them arranged in this trigonal planar arrangement. We call this arrangement trigonal planar arrangement, and the bond angle would be 120 degrees between each of these bonds. So students, it's very important to remember this when it comes to separating out only three repulsive units. The best possible way that we can separate them to minimize the repulsion between them is to arrange them in a trigonal planar arrangement. And when you do that, the angle between each of these repulsive units is going to be 120 degrees. So when it comes to boron trifluoride, electron pair geometry as well as the shape of the molecule happens to be the same because there are no lone pairs in this. So that particular shape is trigonal planar. That shape is trigonal planar. So students, this shape is called the trigonal planar arrangement because you can see you have three of these bond electron pairs or three of these bonds arranged in this particular arrangement with a 120 degree angle between them, and each of these atoms are present in a single plane. So if you place this on a table, you can very clearly see that they are all going to be present in a single plane. There is not a single atom protruding out of the plane or going in to the plane. So therefore, all of these atoms are actually present in a single plane. That's why we call this the trigonal planar arrangement. So now let's move on to the next molecule. Now we are going to be looking at methane molecule. So CH4, methane molecule's Lewis structure is given over here. We can see the central carbon atom surrounded by 4 hydrogen atoms connected to the carbon atom through a covalent bond. So, after observing this Lewis structure, you can see on the carbon atom there aren't any lone pairs of electrons. We have 4 bond electron pairs around the central carbon atom. So, if you take a look at the number of electron pairs that are found around the carbon atom, it's going to be 4 electron pairs found around the central carbon atom is going to be 4. And we don't see any double bonds. Do we see any double bonds, students? We don't. So, therefore, the number of repulsive units around the carbon atom is going to be 4 as well. Number of repulsive units around the carbon atom is going to be 4 as well, and the number of lone pairs is going to be 0. So, when you don't have any lone pairs, we do know that the electron pair geometry and the shape of the molecule happens to be exactly the same. And when it comes to not having any double bond or triple bond, we learned that the total number of electron pairs around the central atom and the number of repulsive units are going to be the same when you don't have multiple bonds stemming from the central atom. We only have single bonds here, so therefore, we do not see a difference in the number of electron pairs around the central atom as well as the repulsive units around the central atom. So, one thing that you should keep in mind is, students, when you are talking about the electron pairs around the central atom, if the central atom does not have any multiple bonds, meaning double or triple bonds, the electron pair number and the repulsive unit number happens to be the same. If the central atom does not have any double bonds or triple bonds, then the electron pair number and the repulsive unit number happens to be the same. In this case, we don't have any double bonds, so the electron pairs around the central atom and the number of repulsive units around the central atom happens to be the same. So, we have 4 repulsive units around the central carbon atom, which means we have 4 electron pairs around a central carbon atom arranged in such a way that minimizes the repulsion between these repulsive units. To represent the carbon atom, we are going to be using a black color ball here from our molecular modeling kit, and this black color ball has 4 holes in it. It has 4 holes in it, and to each of these holes one bond will be connected. So, we will take one connector and connect it to one hole over here. We represent the hydrogen atoms using white color balls. So, we have white color balls with one hole in it, as hydrogen can only form one bond. So, now we have created a hydrogen and a carbon bond. So, black color ball represents the carbon atom, white ball represents the hydrogen atom, and this linker or connecting piece that we have over here represents the bond. And then we can continue to add these carbon hydrogen bonds by connecting these linkers and placing hydrogen atoms. Now, we have 2 carbon hydrogen bonds. We have the third bond connected here, and finally, we have the fourth carbon hydrogen bond connected now. So you can see the 3D structure. So you can see the 3D structure of our methane molecule. Let's place it on the table. So this shape is referred to as the tetrahedral shape. This shape is referred to as the tetrahedral shape. Tetrahedral, and the electron pair geometry is also tetrahedral here. So you can see this makes up a pyramid type of shape. This will be the top of the pyramid, and you can see it is having this tetrahedral shape, producing a pyramid shape with a triangular base. So if you rotate it a little bit, you can very clearly see the tetrahedral shape we are talking about. And regardless of which bond that we keep on top, you are going to see the same shape. That is because each of these bonds are separated with a 109.5 degree angle. 109.5 degree angle. So the bond angle between hydrogen, carbon and hydrogen here is going to be 109.5 degrees. So each of these bond angles happens to be exactly the same, and it produces this tetrahedral shape. Now, when you are trying to draw this structure, unlike the previous two structures, we observed one structure which was angular, which is ozone, and then we moved on to beryllium chloride, which was linear, and then we moved on to boron trifluoride, which was trigonal planar. All of these structures had all of the atoms present in a single plane. We can arrange all of these atoms in a single plane. So, which means you can draw them without any issue in a 2D plane. But this structure has a three-dimensional arrangement when it comes to its atoms. So, it is not going to be easy when you are drawing this in your books to represent the three-dimensional structure. Usually, students, when you draw this, you will be drawing it in the following manner. You will choose two bonds. You will choose two bonds to stay in a single plane. You will choose two bonds to stay in a single plane. If I show it to you like this, let's say these two bonds are in a single plane. And then we say one bond is coming towards you, the other bond is going away from you. Or we say one bond is coming out of the plane while the other bond is going into the plane. So that is how you normally draw this structure. The bond that is coming towards you or out of the plane will be represented by a wedged line, and the bond that is going into the plane or inside or away from you is going to be represented by a dashed line. That is how you would normally represent this 3D shape of the molecule. So students, the very reason why we are doing this practical is to make sure that you understand how each of these atoms are distributed in the 3D space. Because the most that you can do when you are drawing this is to draw a 3D structure with the use of a wedged line and a dashed line. You can't sometimes properly visualize how they are spread in the three-dimensional space. But when we show it to you like this, you should be able to very clearly see how each of these bonds are distributed around the central atom and why we actually use a wedged line and a dashed line to represent bonds that are coming towards you and that are going away from you. Now, we observe the shape of methane. Methane shape was tetrahedral. So, when it comes to this particular molecule, around the central carbon atom, the carbon-hydrogen bonds were distributed in the three-dimensional space to produce this tetrahedral shape. When we were observing molecules like beryllium chloride and we saw boron trifluoride, we saw all of those atoms were distributed in the same plane. None of those atoms were distributed in three-dimensional space. We saw all of them can be represented in the 2D plane. However, when it comes to the tetrahedral molecule, you can very clearly see not all atoms can be represented in a 2D plane. To demonstrate this, we can use a small board that we have over here. If you use this small board and keep 3 of the atoms on the board, you can see only 3 atoms at any given point can come into contact with the plane. There will be 2 atoms that will not be coming into contact with the plane. You can very clearly see here. These 3 atoms are now found on a single plane, but this particular bond, carbon-hydrogen bond that we have over here, is coming towards me and the other bond is going away from me. Or this bond is coming out of the plane and the other bond is going away from the plane. Coming out of the plane and going away from the plane. Now, these are the bonds that you usually draw when you are drawing a 3D structure with the use of a wedged line and a dashed line. You will draw these 2 bonds that are on the plane with just normal lines, and whatever the bond that is coming towards you is going to be represented by a wedged line, and the bond that is going into the plane or away from you is going to be drawn with a dashed line. So now I want you to be very clear about why we use the 3D drawings and why we say the wedged line is representing the bond that is coming towards you, because you can see there are only 3 atoms on the same plane and there are 2 atoms that are not going to be found on the same plane. One carbon-hydrogen bond is actually coming towards you, whereas another carbon-hydrogen bond is going away from you. Since something is coming towards you, since it appears somewhat bigger, we use a wedged line, which is gradually getting bigger towards the hydrogen atom. And we'll be using a dashed line to indicate the carbon-hydrogen bond that is going away from you, because as something goes away from you, it appears smaller or it appears a bit distant. So to indicate that, we use a dashed line. So when you take these tetrahedral molecules, only 3 atoms at any given point can be drawn in a single 2D plane. The other 2 atoms are going to be drawn with the use of a wedged line and a dashed line. Wedged line representing the bond that is coming towards you or out of the plane, and the dashed line represents what is going away from you or into the plane. So you have to understand we can't very clearly give you an idea by just drawing the images on a 2D plane. Sometimes some students find it difficult to visualize how the atoms are arranged in the three-dimensional space. That's why this practical is there in the syllabus, so that you can see how atoms in these kind of 3D shapes are distributed in the three-dimensional space. So this is the shape of our methane molecule. Let's move on to the next molecule now. Now we are going to observe the shape of ammonia, NH3. So you can see over here the Lewis structure of ammonia is given. Ammonia is found on the 5th group, so it has 5 valence electrons, and the valency of ammonia is 3. You can see that there are 3 bonds formed. And apart from the 3 bonds around the nitrogen atom of ammonia, we have 1 lone pair on the nitrogen atom in the ammonia molecule. So when you're talking about the total number of electron pairs around the nitrogen atom, you can see that there are 3 bond electron pairs along with 1 lone pair. So the total number of electron pairs around the central atom over here is 4. And we only have single bonds and lone pairs here. We don't have any double bonds or triple bonds. So therefore, the number of repulsive units around the nitrogen atom happens to be 4 as well. If you had a double bond, this will change. However, since we don't have any double bonds in ammonia, we can see the number of repulsive units are going to be the same as the number of electron pairs around the nitrogen atom in ammonia. And the number of lone pairs happens to be 1. So students, we learned when you have at least 1 lone pair, the electron pair geometry and the shape of the molecule is going to change. Over here, to separate 4 different repulsive units around a central atom, we saw earlier in the methane molecule, we have to acquire a electron pair geometry of tetrahedral shape. So the electron pair geometry around the nitrogen atom in ammonia is going to be tetrahedral. All of these electron pairs are separated as far away as possible by acquiring this tetrahedral electron pair geometry. However, one of these electron pairs is a lone pair. So when you are observing the shape of the ammonia molecule, the shape is going to be trigonal pyramidal. It's going to have a trigonal pyramidal shape. So let's observe this particular shape of ammonia. Usually, nitrogen is represented by a blue color ball in molecular modeling kits. So we will be using this blue color ball as it has the correct color as well as the correct number of holes needed for this particular shape that we are trying to show here. So over here in the ammonia molecule, we have 3 nitrogen-hydrogen bonds. So let's start with 1 nitrogen-hydrogen bond. So we have the nitrogen atom represented in this blue color. Now we have connected a linker which represents a bond, and hydrogen is represented with a white color ball. So let's connect the hydrogen atom as well. And we have another linker, and to that we can connect another white color ball representing a hydrogen atom. So we have now 2 nitrogen-hydrogen bonds, And finally, we can insert the third nitrogen-hydrogen bond like so. Now students, this is the shape of the ammonia molecule. This is the shape of the ammonia molecule. Now this shape is known as trigonal pyramidal. You can see it is not flat. The nitrogen atom of the ammonia molecule is going to be above the 3 atoms of hydrogens. If hydrogen atoms are in a single plane, we can see the nitrogen atom is above that particular plane. So this shape is known as trigonal pyramidal shape. Now let's observe why this shape exists. Now let's only include the electron pairs. Now around the nitrogen atom over here, there are 4 electron pairs. So to represent the last electron pair, let's include this linker. Now you can see we have the nitrogen atom, and around the nitrogen atom there are 4 electron pairs. Out of these 4, only 3 are bond electron pairs. So we can choose any electron pair and we can keep it as a lone pair, and we can connect 3 hydrogen atoms to the other 3 electron pairs and make them bond electron pairs. Now we can see there are 3 bond electron pairs, and this remaining linker will represent the non-bonding electron pair, which is our lone pair. So students, lone pairs are normally not indicated in a modeling kit like this. So therefore, if you remove that linker that I included earlier, you get to the shape of the ammonia molecule, which happens to be trigonal pyramidal. Now students, we saw when we have a lone pair, how it contributes to creating this trigonal pyramidal shape. As I have mentioned earlier, when you have a lone pair, it exerts a greater repulsion to each of these bond electron pairs we have here. Lone pair bond pair repulsion is going to be greater than bond pair repulsion. So because of that, these bonds are going to be further repelled away from the lone pair, and this decreases the bond angle between hydrogen, nitrogen, hydrogen bonds. So between 2 nitrogen, hydrogen bonds, the bond angle will be decreased due to the lone pair exerting a greater repulsion to this bond pair of electrons. So all of these bond pair of electrons actually will be repelled away from the lone pair, creating a smaller bond angle. And normally when you have a tetrahedral shape, the bond angle we observed earlier is going to be 109.5. The bond angle between carbon hydrogen bonds in the methane molecule we observed is 109.5. When it comes to the ammonia molecule, we do have a tetrahedral electron pair geometry. However, when this tetrahedral electron pair geometry produces this trigonal pyramidal shape, the bond angle between each of the hydrogen-nitrogen bonds is not going to be exactly 109.5. Due to the lone pair exerting a greater repulsion, these nitrogen-hydrogen bonds will come together a little, decreasing the bond angle. So therefore, the bond angle between nitrogen-hydrogen bonds are going to be less than 109.5. Not 109.5, it is going to be less than that, slightly less than 109.5. So you have to keep that in mind, students. Just because this particular shape was stemming from a tetrahedral electron pair geometry doesn't mean we are going to be seeing a 109.5 bond angle over here. Instead, we will be having a smaller bond angle than that due to the presence of the lone pair. So that is the shape of ammonia molecule. Let's take a look at our next molecule. We'll be taking a look at water in this part of our experiment. Water is a very familiar substance for all of us, and we'll be using water for many reactions, and I'm quite certain majority of you already know the shape of water and the Lewis structure of water and its electron pair geometry and all the information that revolves around the shape of the water molecule. I'm certain that you already know. However, let's take a look at the shape of the water molecule with the use of our molecular modeling kit. So before we go into that, like we did in the previous molecules, let's observe the details about the water molecule as well. Water molecule has the central atom oxygen in it, and you can see around the oxygen atom there are 2 bond electron pairs and 2 lone pairs. So altogether, how many electron pairs are there around oxygen? There will be 4 electron pairs around the oxygen atom. And if you take a look at the total number of repulsive units around the oxygen atom, since we don't have any double bonds here, we have a total of 4 repulsive units around the oxygen atoms. And the number of lone pairs happens to be 2. We can very clearly see that there are 2 lone pairs. What does that mean? The electron pair geometry and the shape of the molecule will not be the same. So electron pair geometry happens to be tetrahedral, meaning electron pairs that we observed around the oxygen atom is distributed around the oxygen atom in a tetrahedral arrangement. And the shape of the molecule happens to be angular. Usually, students, oxygen atoms are represented in a red color. However, depending on the molecular modeling kit you are using, you have to choose a suitable ball with a suitable number of holes in it. Now, we have chosen this black ball to represent the oxygen atom, and hydrogen atoms will be represented by the white color balls. So, first of all, let's insert all of the electron pairs around oxygen. Now, I have taken 4 linkers here to represent 4 electron pairs. And how are the electron pairs distributed around the oxygen atom? It is distributed in a tetrahedral arrangement. So this particular ball allows us to get to that tetrahedral arrangement because there are only 4 holes in this ball. We can see we have now added these linkers that are currently representing our electron pairs, and we can see that they are distributed in a tetrahedral arrangement. So keep in mind, when I inserted these linkers, I wanted to represent only the electron pairs, and these represent both the bond electron pairs and the lone pairs. So what is the electron pair geometry? It is tetrahedral. Now, let's connect 2 hydrogens to these electron pairs. and convert these electron pairs into bond electron pairs. So now when I connected one hydrogen atom here, this oxygen and hydrogen together has formed an oxygen hydrogen bond. So this is now a bond electron pair. Over here we have another bond electron pair now. These two will represent the lone pairs. You can see how in a water molecule the lone pairs are distributed now. If you take the water molecule, hydrogen, oxygen and hydrogen is going to have this particular bent arrangement, and the lone pairs are going to be present like this. Whenever you are showing the shape of the molecule, we are not going to include the lone pairs. So the shape of the molecule is going to be this bent shape. We call this angular shape. And all of these atoms can be represented in a single plane. None of the atoms actually protrude out of this plane. So therefore, this is all three of these atoms are on the same plane. So therefore, this bent shape is going to be represented like this, and we are going to note that there aren't any atoms coming out of the 2D plane. So we can lie it flat on the table. You can't see any atoms protruding out of the plane or going into the plane. So what you see here is our water molecule. Now students, before we move any further, if I remove these hydrogen atoms again and connect these linkers to represent the electron pair geometry, when you have this tetrahedral electron pair geometry, angle between each of these repulsive units is going to be 109.5. But after converting these electron pairs into bond electron pairs, you will see this molecule now has 2 bond electron pairs and 2 lone pairs. Now these lone pairs have greater mobility, and so therefore they are distributed in a greater spatial volume. They can apply a greater repulsion on these bonds that we have over here, which will make these bonds actually come closer to one another, creating a smaller bond angle, right? Although when we try to bring them closer, what happens is this bonds bending, but what actually happens is these bonds will come closer to one another in a straight manner, not just bend like this. So the bonds will actually come closer to one another, creating a smaller bond angle between them. So the bond angle of the hydrogen-oxygen bonds in the water molecule is going to be less than 109.5. So it's going to be quite small, even smaller than the bond angle observed in ammonia. We saw when it comes to ammonia also, due to the lone pair that was present, the bond angle was reduced. But in this case, you can see the bond angle is going to be further reduced due to 2 lone pairs being present. When it comes to the ammonia molecule, the electron pair geometry was tetrahedral due to the presence of 4 electron pairs around central atom. When it comes to the water molecule, we have 4 electron pairs around the central atom, but 2 lone pairs are present compared to ammonia. Ammonia had only 1 lone pair. When it comes to water, oxygen has 2 lone pairs. So the 2 lone pairs exert a greater repulsion, so the bond angle is going to be slightly smaller. So this is the shape of the water molecule. So due to the greater repulsion exerted from 2 lone pairs, the bond angle over here is going to be further reduced, and the actual bond angle over here is not going to be 109.5, it's going to be 104.5. Now, if you don't have any lone pairs when it comes to tetrahedral electron pair geometry, at that point the shape of the molecule will have the tetrahedral shape itself, and the bond angle is going to be 109.5. Methane is a good example. Methane had a bond angle between its carbon-hydrogen bonds of 109.5. Then when it comes to ammonia, we saw there were 4 altogether electron pairs, and one of the electron pairs was a lone pair. So therefore, at that point, the resultant shape was trigonal pyramidal, and the 109 point bond angle got reduced a little bit due to the presence of a lone pair. And I told you the bond angle is no longer going to be 109.5, it is slightly reduced, and that value is going to be 107. And when it comes to water, we have 2 lone pairs, and the electron pair geometry of water molecule also is going to be tetrahedral, just like in ammonia and as well as in methane. All of them have the same electron pair geometry. Only difference between these 3 molecules is that methane didn't have any lone pairs, ammonia has 1 lone pair, and water has 2 lone pairs. So depending on the number of lone pairs you have, the bond angle will be decreasing, and over here now the current bond angle between the hydrogen-oxygen hydrogen bond is going to be 104.5. So that concludes the information about the shape of the water molecule. We can now move on to our next molecule. Now we are going to be looking at the PCl3 molecule. So in the PCl3 molecule, we can see around the phosphorus atom there are 3 chlorine atoms bonded to the phosphorus atom. We can see the Lewis structure of PCl3 here, and we can see that around this central phosphorus atom there are 3 bond electron pairs and 1 lone pair. 3 bond electron pairs and 1 lone pair. So when you are talking about the number of electron pairs around the central atom, that is going to be 4. We don't have any double bonds here. When it comes to talking about the number of repulsive units around the central atom, that is also going to be 4. And number of lone pairs around the central atom is going to be, number of lone pairs around the central atom is going to be 1. So the electron pair geometry is going to be tetrahedral, and when you have 1 lone pair in a tetrahedral electron pair geometry, what is the shape that you produce? Trigonal pyramidal. You are going to produce a shape known as the trigonal pyramidal shape. We observe this same shape when it comes to ammonia. So let's construct this shape with the use of our molecular modeling kit. In order to make this shape, we need to take a ball that has 4 holes in it, and we have this blue color ball that has 4 holes in it, and we are going to be using this to represent the phosphorus atom, and the Cl atoms in this case will be represented by a yellow ball. So we now connect our linkers over here. Usually students, we use green color balls to represent chlorine atoms. However, if you have only yellow balls, then at that point you can use them to represent Cl atoms, as long as you know what each color represents in the model that you are creating, you can actually identify the shape of the molecule based on what you see after connecting the bonds and the atoms together. So now we have a chlorine atom connected to a phosphorus atom, and we can see the chlorine phosphorus bond. And then we can see, if you connect another linker and connect another chlorine atom, now we have two chlorine phosphorus bonds, and to another hole of the phosphorus atom we can connect another yellow ball, and we form this trigonal pyramidal shape. We form this trigonal pyramidal shape. So students, you can very clearly see we observed a similar shape when it comes to ammonia as well. Over here what you observe is PCl3, phosphorus trichloride. Again, if you want to very clearly observe the electron pair geometry of this, we can connect another linker and remove these atoms, and this happens to be our electron pair geometry. There are 4 electron pairs. Out of them, one is going to be a lone pair. So if you don't connect any atoms to it and connect atoms to all the other electron pairs, we can again get to the same shape that we were talking about earlier. Now we can see there are 3 bond electron pairs and 1 lone pair. This is our lone pair. Normally we don't visualize the lone pair with the linker, just wanted to give you an idea. So when you remove this lone pair, you can see the trigonal pyramidal shape of PCl3. Like I mentioned earlier, when you have the tetrahedral shape, the angle between every repulsive unit is going to be 109.5. However, when you're talking about the shape of the molecule, you can see there's one lone pair here, which is different, which has a different spatial volume or different spatial distribution compared to the bond electron pairs. So therefore, they exert a greater repulsion to all of these 3 other bonds that are present here, creating a shorter distance between the bonds, or bonds will come closer to one another. When these bonds come closer to one another, the bond angle between each of these bonds will reduce from 109.5 to a smaller bond angle. So the bond angle that you see between the chlorine, phosphorus and chlorine atoms over here is not going to be 109.5. It is going to be smaller than 109.5, as I have explained earlier. This is due to the presence of this lone pair over here. Now, with that in mind, we can move on to our next molecule. Now students, before we move on to sulfur hexafluoride, our next molecule, we are going to observe what are the different molecules that have the same tetrahedral electron pair geometry but different shapes. So let's take a look at the methane molecule. We observed this earlier. Methane molecule has 4 repulsive units around it, but no lone pairs. All of the 4 repulsive units are bond electron pairs. So their electron pair geometry and shape of the molecule happens to be the same. And what is the electron pair geometry when you only have 4 repulsive units? Tetrahedral. So the methane molecule is having electron pair geometry which is tetrahedral, and the shape of the molecule is also tetrahedral. When it comes to phosphorus trichloride, PCl3, it has the same electron pair geometry which is tetrahedral, but it has one lone pair and 3 bond pairs. So therefore, it doesn't have the same shape as the electron pair geometry. Electron pair geometry is tetrahedral, but the shape is different due to one of the repulsive units being a lone pair. Out of the 4 repulsive units seen in this tetrahedral electron pair geometry, one is a lone pair, which gives us the trigonal pyramidal shape. And finally, we can move on to water molecule, where we have the same tetrahedral electron pair geometry, but now we have 2 lone pairs. So when you have 2 lone pairs, the shape is going to be angular. So in this summary, we are seeing when we start with the same electron pair geometry and we gradually replace each of the bond electron pairs with lone pairs, how the shape is changing. So we can see over here, if you direct your attention to the molecules that we have constructed and demonstrated over here, we have the methane molecule which has the tetrahedral shape to the molecule. All of the repulsive units are bond electron pairs. So therefore, the shape of the methane molecule happens to be tetrahedral. Then we have the PCl3 molecule, phosphorus trichloride. So we can see there are 3 bond pairs, but one is going to be a lone pair. So because of that, the resultant shape is going to be trigonal pyramidal. So methane molecule and the PCl3 molecule both have the same electron pair geometry, which is tetrahedral. But when it comes to PCl3, one repulsive unit is going to be a lone pair. So therefore, the shape is trigonal pyramidal. And finally, we have our water molecule. You can see water molecule has an angular shape. We call it an angular shape, but we also use the word bent shape. So red color ball over here represents the oxygen, and 2 hydrogens are represented by the 2 white color balls. Over here around the oxygen atom, the electron pair geometry happens to be exactly the same as the electron pair geometry of PCl3 and methane or CH4. They have the same electron pair geometry. Methane doesn't have any lone pairs. PCl3 has 1 lone pair, and when it comes to oxygen in the water molecule, it has 2 lone pairs. That is why you observe this bent shape. We saw there are 2 lone pairs coming out of the oxygen atom. So therefore, we have this bent shape. So this summary is brought about to tell you that depending on how many lone pairs are found in a similar electron pair geometry, the shape that we observe will vary. Good example is methane is tetrahedral. It has the electron pair geometry which is tetrahedral. When it comes to PCl3, it has the same electron pair geometry, tetrahedral, but it has a single lone pair resulting in a trigonal pyramidal shape. Water, the oxygen's electron pair geometry is tetrahedral. However, since it has 2 lone pairs, the shape is different to all the other 2. The shape is going to be bent, or it is also referred to as an angular shape. So you can very clearly observe how we gradually, when we gradually increase the number of lone pairs, how the shape is changing. So after observing the different shapes of methane, phosphorus trichloride and water, we can now move on to our next molecule. Now students, let's take a look at sulfur hexafluoride SF6. Do we have any lone pairs on sulfur? No. So when you are counting the total number of electron pairs around sulfur, that is going to be 6. The total number of repulsive units around sulfur is going to be 6 here, because you don't have any double bonds in this molecule. Do we have any lone pairs? No, which means electron pair geometry and the shape of the molecule will be the same. And we can see the electron pair geometry is octahedral and the shape of the molecule is also octahedral. When it comes to distributing 6 repulsive units around a central atom, to minimize repulsion between them, you need to arrange them in an octahedral arrangement. Let's observe this using these gray color balls as the central atom. In this case, sulfur is going to be represented by this gray color ball, and fluorine atoms will be represented by yellow color smaller balls. Let's connect these linkers that we have over here, or connectors, and let's consider them to be electron pairs. So when you have 6 electron pairs, they are going to be arranged around the central atom in this octahedral arrangement. So the electron pair geometry can be seen over here. Now these are just the linkers without the atoms connected to it, so we can assume that these are just electron pairs. So these electron pairs around the central atom has this octahedral arrangement, or we can say this is the electron pair geometry of SF6. So if you connect the atoms now, we can observe the shape of sulfur hexafluoride. Now we can see the shape of the molecule, and this shape is going to be known as octahedral shape. This is the octahedral shape, and in this shape you can see there are 4 fluorine atoms, and this central atom, which is the sulfur atom, are going to be in a single plane, and above the plane we can find 1 fluorine atom, and below that plane we can find another fluorine atom. So if you take a look at these 3 atoms, the fluorine atom above the plane, sulfur atom, which is the central atom, and the fluorine atom below the plane are going to be found in a straight line, and we have 4 fluorine atoms and 1 central atom, which is the sulfur atom here, in 1 2D plane. So there are 4 fluorine atoms in 1 plane, and above that plane you have 1 fluorine atom, and below that plane you have another fluorine atom. This arrangement is known as the octahedral arrangement. And between each of these bonds, the bond angle would be 90 degrees. The bond angle is exactly 90 degrees. And between each of the bonds on the same plane that we spoke of earlier, there also you see that that the bond angle is exactly 90 degrees. So if you turn it like this, you can see the bond angle is exactly 90 degrees. If this is the plane we are talking about, right? Well, we were talking about this plane earlier, where all the fluorine atoms, 4 fluorine atoms and the sulfur atoms are lined together in this 2D plane, and the bond angle between each of those bonds also happen to be 90 degrees. So when it comes to this sulfur hexafluoride molecule, the shape of it is going to be octahedral, and the bond angle between each of these bonds are going to be exactly 90 degrees. So students, now we have observed the shape of sulfur hexafluoride SF6, and we observe the shape of SF6 is octahedral. So now it's time to move on to our next molecule. Now students, we are going to be moving on to our next molecule, SF4, or sulfur tetrafluoride. Sulfur tetrafluoride. So you can see the Lewis structure of sulfur tetrafluoride here. We can see around the central atom sulfur, there are 4 bond electron pairs. Since there are 4 bonds, we have 4 bond electron pairs, and we have 1 lone pair here. 4 bond electron pairs and 1 lone pair here. Altogether, around the sulfur atom here, we have a total of 5 electron pairs. So that's what we have mentioned here. Around the central atom, in the valence shell, we have 5 electron pairs, and the number of repulsive units around the sulfur atom happens to be the same as the number of electron pairs around sulfur, because we don't have any double bonds or triple bonds here. So we can see both of these numbers are the same. So the number of repulsive units also happen to be exactly 5. There is 1 lone pair and 4 electron pairs. So therefore, the number of lone pairs around sulfur is going to be 1. This indicates the electron pair geometry and the shape of this molecule are not going to align with one another, as electron pair geometry would be trigonal bipyramidal, and the shape of this is going to be distorted seesaw shape. So to observe these shapes, we can move on to our molecular modeling kit. But students, keep in mind, when it comes to electron pair geometry of a molecule that contains 5 repulsive units around it, is going to be trigonal bipyramidal. Meaning, to obtain the minimum repulsion between each of these repulsive units, when you have 5 repulsive units only in a molecule, they will acquire this trigonal bipyramidal electron pair geometry. Now students, to represent this trigonal bipyramidal electron pair geometry, I can use this gray color ball which has 5 holes in it. And to represent electron pairs, I am going to use these connectors. So when it comes to this trigonal bipyramidal shape, there will be 3 electron pairs on the same plane distributed with a 120 degree angle. So between these 2 electron pairs, the angle would be 120 degrees. And these 3 electron pairs are going to be on the same plane. And there will be 1 electron pair above that plane and another electron pair below that plane. So now we have altogether 5 electron pairs around the sulfur atom, and this particular electron pair geometry is known as trigonal bipyramidal electron pair geometry. We are of course assuming each of these connectors represent electron pairs around the sulfur atom. Now let's see, when we connect fluorine atoms, how we are going to be connecting fluorine atoms to make sure the repulsion between the bond pairs and the lone pair bond pairs remain a minimum. So imagine you connected the 4 fluorine atoms in the following manner. If you connect the 4 fluorine atoms in the following manner and form the sulfur tetrafluoride molecule like this, you can see each of these fluorine and sulfur bonds that we have over here are going to be separated with a 120-degree angle, which means there's very minimum amount of repulsion between them because they are well separated with a larger angle. But if you observe the separation of these 2 bonds, the bond angle between this particular sulfur fluorine bond and sulfur fluorine bond that we have over here is going to be 90 degrees. So the bond angle over here is smaller. Now, in a similar position, we have placed our lone pair. This linker without atom connected to it represents the lone pair. So this lone pair and the bond pair angle is also 90 degrees. And we know lone pairs exert a greater repulsion on all the other electron pairs around it. So placing a lone pair in a position where the angle between the lone pair and the bond pairs are smaller is not going to create a more stable molecule, because this repulsion is greater and these bonds will be bent quite a bit thanks to the repulsion that is going to be exerted by the lone pair here. Therefore, having the lone pair over here where there is a smaller angle between the lone pair and the bond electrons is going to be not very stable. So we will have to disconnect one of these atoms and connect it over here. Now when you do that, you can very clearly see when we have the lone pair here, the bond angle between this lone pair and the bond electrons over here is going to be 120. In actuality, it's going to be slightly greater than 120. Over on this side also, it's going to be 120. There's going to be only 2 bonds with 90-degree bond angle close to the lone pair. If it was in the previous position, all 3 of these bond electron pairs are going to be close to the lone pair and they will have a 90-degree bond angle with all 3 of these bonds. But when we have the atom placed over here and when we have the lone pair present over here, you can see at that point the bond angle between 2 of the electron pairs or bond electron pairs are going to be 120 degrees. You can see over here it's 120 degrees, and with the other 2 it's going to be 90 degrees. This is a more stable arrangement, or this is a more stable position to place our lone pair because it can exert a stronger repulsion. So therefore, placing the lone pair over here in a position like this brings the molecule more of a stability. So therefore, this is where the lone pair is going to be. And if you remove the lone pair to see the shape of the molecule, you can see the shape of the molecule appears to be like a seesaw. This appears to be like a seesaw. You can see it appears to be like a seesaw. So Although we say that this is having a seesaw shape, keep in mind there is still a lone pair of electrons over here, which does distort the shape a little bit by bringing these two bonds slightly below like this, right? These two bonds will be repelled so that they actually move down a little bit. It doesn't bend like this, but this entire straight bond will move down a little bit. It doesn't bend like this. Instead, it actually moves down a little bit. So when that happens, we don't have a very clear seesaw shape. So we call this distorted seesaw shape. So the shape of sulfur tetrafluoride is going to be distorted seesaw. So it is very important to know the shape of such molecules. And if you are looking into the bond angle between these two bonds, we have few different bond angles here. The bond angle between these two bonds is going to be 120 if the lone pair was replaced with a bond. But since there is a lone pair over here, the bond angle is slightly smaller than 120. And the bond angle between these two usually should be 90 degrees, but as these bonds come down a little bit, the bond angle will be slightly smaller than that, and the bond angle between these two bonds should be 180 when there is no lone pair. But when there is a lone pair present, since they come down a little bit like this, the bond angle slightly changes below 180 degrees. So it's not exactly 180, it is somewhat smaller than 180. So students, this is the shape of sulfur tetrafluoride molecule, and it was distorted seesaw shape. Now after observing this distorted seesaw shape, we are now going to move on to our next molecule. Now students, we move on to chlorine trifluoride, ClF3. So you can see in this molecule, the Lewis structure of the molecule is here. We can see around the central atom chlorine, there are 3 bond electron pairs, as there are 3 bonds, and there are 2 lone pairs. Altogether, how many electron pairs are around the chlorine atom? Just like in the previous molecule that we observed, the number of electron pairs around this particular central atom also happens to be exactly 5. And since we don't have any double bonds, the number of repulsive units also happen to be 5. However, we have 2 lone pairs here. In the previous molecule, sulfur tetrafluoride, we had only 1 lone pair. Since we have in both of these molecules the same number of repulsive units, the electron pair geometry around the central atom is going to be trigonal bipyramidal. In sulfur tetrafluoride, there was 1 lone pair and resulted in forming a distorted seesaw shape. And in this case, we have 2 lone pairs, which will result in forming a shape known as distorted T shape. So to represent this particular shape, we are going to be taking the same gray color ball that we used earlier, and we are going to use these connectors to represent the electron pairs around the central atom. Now when you place the electron pairs around the central atom like this, you can see all 3 of these electron pairs are in a single plane, and the angle between these electron pairs are going to be 120 degrees, meaning there's a greater separation between these 2 electron pairs and the repulsion is minimized due to this 120 degree larger bond angle seen between these 3 electron pairs. The next electron pair actually the next 2 electron pairs we are going to add to this are going to be added above and below the plane of those 3 electron pairs that we spoke about earlier. When we add electron pair above and below, you can see these electron pairs are quite closer to the adjacent electron pairs, and the bond angle between them is going to be just 90 degrees. So these electron pairs are somewhat closer to one another, having a smaller angle between them, causing them to have somewhat of a greater repulsion between them. As electron pairs come closer together, the repulsion between them is obviously going to be greater. So over here also we can see 90-degree angle. So when you have these 2 electron pairs connected above and below like this, there will be greater repulsion experienced by these electron pairs. So when you are placing the lone pair, or when it comes to this particular molecule, all of these 6 electron pairs are not going to be connected to another atom to form bond electron pairs. We know that there are only 3 bond electron pairs, and the rest of the 2 electron pairs are lone pairs. So you have to think and analyze and then decide where you are going to be placing these lone pairs so that this molecule becomes more stable. If you place the lone pair above these 3 bonds, the lone pair can exert a greater amount of repulsion and it can cause a bit of an instability when you have such a small bond angle or such a small angle between the lone pair and the bond electron pairs. They tend to be a bit more unstable. But instead of placing a lone pair in position like this, if you place a lone pair in a position such as this one, you can see the angle between the adjacent electron pairs have now improved a little. The angle is going to be 120-degree angle. Yes, there will be a 90-degree angle over here, but only 2 electron pairs are going to be present with that particular angle. So placing lone pairs of electrons in a position where there is a greater bond angle is going to contribute to having a higher stability. So it is better to have 2 lone pairs in 2 positions like this, where the bond angle between them is greater. If you have lone pairs in 2 positions like this, the bond angle between them is going to be so small, around 90 degrees. So there will be a greater repulsion resulting in greater instability. If you have it in 2 positions like this, the repulsion is going to be smaller between the lone pairs because there will be a greater bond angle. So we can keep these 2 as our lone pairs. So we can proceed to include our fluorine atoms, which are going to be represented by these yellow color atoms like this. Now, if you observe here, these are going to be your bond electron pairs, and these 2 other connectors are going to be our lone pairs represented. So there are 2 lone pairs and 3 bond pairs of electrons. Now when you are showing the shape of the molecule, we will not include the lone pairs of electrons. So you can now see the shape of the molecule is going to be T-shaped. We say the shape of the molecule is T-shaped. However, due to the presence of the 2 lone pairs, these 2 bonds slightly come down, creating a distorted T-shape. So we don't just say it is a T-shape because there are 2 lone pairs here that will exert a certain amount of repulsion to these bond electron pairs and will create a little bit of a distorted T-shape. And it will create a bit of a distorted T-shape like this. So the bond angle over here is not going to be exactly 90 degrees. Instead, it is going to slightly decrease due to these two bonds being pulled down due to the repulsion that is there when two lone pairs are present over here in these two locations. So due to these lone pairs, these two bonds will slightly come down, creating a smaller bond angle between these two bonds. So students, this is going to be the shape known as distorted T shape. The electron pair geometry of chlorine tetrafluoride is going to be trigonal bipyramidal. However, since there are two lone pairs in this molecule, the molecular shape happens to be distorted T shape. Now, let's move on to the next molecule. So students, we are going to be now moving on to xenon difluoride or XeF2 xenon difluoride. And the Lewis structure of xenon difluoride is given here. You can see around the xenon, which is the central atom, we have two bonds and three lone pairs. So the two bonds bring in two bond electron pairs, and since there are three lone pairs, the overall number of electrons around the xenon atom is going to be 5. So there are 5 electrons around the xenon atom, and we have overall 5 repulsive units around xenon as well. So apart from these two details, one of the more important details that we can see over here is the number of lone pairs that we see here. There are 3 lone pairs around the central atom. We do understand when the number of repulsive units have certain amount of lone pairs in it, we do know that the electron pair geometry and the shape of the molecule are not going to be the same. Just like in the previous two molecules we observed, the electron pair geometry, when 5 repulsive units are present around a central atom, is going to be trigonal bipyramidal. And the shape of this particular molecule, because there are 3 lone pairs, is going to be linear. So this is going to be a linear molecule. So now, with the use of the same gray color ball that we used earlier, we can demonstrate the shape of this molecule. Just like we did earlier, we can use these links or linkers to show the electron pairs first. We can connect these electron pairs in a single plane like this. So these 3 electron pairs are connected in a single plane, and the bond angle between them is 120 degrees. So they have a larger separation. When you have 2 other electron pairs connected to the same central atom, they will acquire this trigonal bipyramidal electron pair geometry. After connecting these electron pairs, you can see that these 2 electron pairs have a smaller angle between them. So when considering the electron pairs that were found on the horizontal plane, we have a smaller bond angle here. The electron pairs that were found on the same plane had a 120 degree bond angle between them. You can see the bond angle was greater, but when you're talking about these electron pairs, it is going to be just a 90 degree bond angle. So when you are placing 3 lone pairs onto this electron pair geometry, where is it going to be placed so that the repulsion between these lone pairs and lone pairs are going to be minimal? If you place lone pairs in these axial positions, you will see they will be very close to other electron pairs, and the repulsion between lone pairs, since is going to be greater, having a lone pair in such an axial position is going to create an unstable molecule. So it is always better to include all of these lone pairs in this horizontal plane, where each of the lone pairs are going to be separated with a greater angle, which is 120-degree angle. So students, when you are placing your lone pairs, it is better to place the lone pairs with a greater angle between them. So after realizing that, we can now move on to adding our fluorine atoms. So we will add one fluorine atom over here, and another fluorine atom should be added over here to produce a stable molecule. We can see at this point the lone pairs have a greater angle between them, which will increase the stability of this molecule. If by any chance, if you make the structure like this, you can see there are going to be lone pairs that are having a very small angle between them. This will create a greater repulsion between them, which would cause the formation of an unstable molecule. So you are not supposed to place lone pairs with a smaller angle like this. If there is a possibility to increase the angle between the lone pairs, you should take that option, so that the molecule that is formed is going to be a more stable molecule. So when you are drawing molecules, or when you are trying to remember what is the most stable configuration to arrange these atoms, when you have 5 repulsive units and 3 lone pairs, you have to think about why we place the lone pairs in the horizontal axis, where there are 3 lone pairs going to be in the same plane. And that is mainly to have a greater angle between the lone pairs, so that we can minimize the repulsion between them. So this is the shape of the XeF2 molecule. To clearly observe this shape, we can remove these lone pairs and only retain our bond electron pairs and the atoms. You can now see the shape of xenon difluoride, XeF2. So after observing this linear shape of xenon difluoride, we can now move on to the next molecule. The molecule we are going to be looking at now is xenon trifluoride, XeF4. The Lewis structure of this molecule is given over here. We can see around the central atom xenon, we have 4 bonds, bringing in 4 bond electron pairs and 2 lone pairs. Altogether, the number of electron pairs around xenon is going to be 6. Since there aren't any double bonds or triple bonds around xenon, the number of repulsive units are also going to be 6. And we saw the number of lone pairs are going to be 2. So therefore, you can see the number of lone pairs of electrons around the central atom is going to be 2. When you have 6 electron pairs around a central atom, we saw earlier how the central atom is going to arrange these electron pairs around it. That particular electron pair geometry is going to be known as octahedral electron pair geometry. When you have 6 electron pairs or 6 repulsive units around the central atom, the electron pair geometry that we acquire is going to be known as the octahedral electron pair geometry. After observing that the electron pair geometry is octahedral, we will notice that there are 2 lone pairs in this molecule, meaning the shape of the molecule is not going to be octahedral. We have to carefully place these two lone pairs in two positions, which will maximize the distance between these two lone pairs and minimize the repulsion between the lone pairs. When you arrange the lone pairs in such a manner, the shape of the molecule that we are going to observe is known as square planar shape. Let's observe this shape by using another gray color ball which has 6 holes in it. Earlier we used a gray color ball which had only 5 holes in it. This particular gray color ball has 6 holes in it. And we will connect these linkers to this gray color ball, and these linkers currently will represent the electron pairs. Now we can see when we connect these 4 linkers are going to be found on a single plane separated from a 90-degree angle between them. And after that, we are going to place another link above that plane and another one below that plane. So we have now produced our octahedral electron pair geometry. Now it is time for us to decide where we are going to be placing the 2 lone pairs. If you place the 2 lone pairs into adjacent locations like this, since lone pair repulsion is much greater, the molecule will be unstable. So you should not be placing 2 lone pairs close to one another like this. You can either place the lone pair over here and over here, which is basically 180-degree separation between the 2 lone pairs, or you can use the top link over here to represent the lone pair, and another lone pair can be placed over here, again 180-degree separation. So let's do that and observe the shape of the molecule. So we are going to be using again yellow color balls to represent our fluorine atoms. Now you can see at this point the 2 lone pairs are further away from one another, so therefore the lone pair repulsion is going to be controlled, and therefore the molecule is going to be more stable. And the shape of the molecule is going to be known as square planar. That is because all of these four fluorine atoms are going to be found in a single plane. And above and below the plane, you will have 2 lone pairs. Now imagine if you incorrectly formed this molecule and placed the 2 lone pairs adjacent to one another like this. At that point, there's going to be a greater repulsion between them because of the close proximity of the 2 lone pairs, and therefore this molecule will be unstable. To avoid this, we can place the 2 lone pairs opposite one another so that there is a 180-degree angle between these 2 lone pairs. As I mentioned throughout the previous examples, we should not be including the lone pairs when observing the color of the molecule. This particular molecule has the shape square planar. You can see when you connect these atoms together, you form a square, and this 4 fluorine atoms and the central atom is going to be present on a single plane. So therefore, we call this arrangement the square planar arrangement, or we call this shape the square planar shape. When you place it on a table, we can very clearly see how all 5 of these atoms are going to be in a single plane. None of the atoms are coming out of the plane or going inside the plane. So this is the shape of our xenon tetrafluoride, and the bond angle between each of these bond electron pairs or each of these bonds are going to be 90 degrees. The bond angle is going to be 90 degrees. Although there is a lone pair over here repelling these bonds downwards like this, but at the same time there's going to be another lone pair that is going to be repelling these bond electrons upwards. So their repulsions actually get cancelled off, and you can see all of the bond electron pairs are going to be found on a single 2D plane. So this is going to be a square planar shape. After observing the shape of this xenon tetrafluoride molecule, we are going to now move on to our next molecule. Now we will observe the shape of IF5, iodine pentafluoride. So the Lewis structure of IF5 is given here. Around the central atom iodine, we have 5 bonds bringing in 5 bonding electron pairs or 5 bond electron pairs, and there's 1 lone pair over here. So the overall number of electron pairs around iodine happens to be 6. 5 bond electron pairs and 1 lone pair. Since there aren't any double bonds, the total number of repulsive units also happens to be 6. And we can very clearly observe there is a lone pair on the central atom. So the number of lone pairs is going to be 1. The electron pair geometry, when there are 6 electron pairs around a central atom, is octahedral. We observed this earlier. And when there is only 1 lone pair, the shape of the molecule is going to be distorted square pyramidal. To demonstrate this, we will be using a gray color ball that has 6 holes in it. As I did in the previous instances, we can connect these linkers and indicate the electron pair geometry first. So this is the octahedral electron pair geometry. Out of these 6 electron pairs, 1 happens to be a lone pair. So all of these electron pairs are separated with a 90-degree angle. So you can choose any electron pair among these and consider it to be a lone pair. It doesn't matter which one you choose because all of them are going to be separated with a 90-degree angle. So let's say you want to consider this to be the lone pair. You can consider it to be the lone pair, and the rest of it can be the bonding electrons. So let's consider the top linker to be our lone pair, and the others we'll consider them to be our bonding electron pairs, and fluorine atoms are going to be represented with this yellow color ball. So fluorine atoms are going to be connected to all the other linkers, creating iodine fluorine bonds. And this happens to be the resultant shape. And this shape, you can see, has 4 fluorine atoms and the central atom at the bottom of this molecule, and on the top you have only 1 molecule. gives you a pyramidal shape. But the base of the pyramid appears to be a square. If you connect these four atoms together, you can see it's a square. So the base of the pyramid appears to be a square, and this top atom will be the top of the pyramid. So therefore, the shape is usually known as square pyramidal. However, students, something that we shouldn't forget is the fact that there is a lone pair at the bottom here. This lone pair acquires a greater spatial volume and therefore exerts a greater repulsion on these bond electron pairs. So when that happens, this shape is going to be distorted a little bit, or else I can indicate it like this. Due to the presence of the lone pair, these bond electron pairs will be getting closer to one another by moving a bit downwards. So if I try to stimulate that, this is the type of thing that will happen due to the repulsion of the lone pair. The bond doesn't bend like this when the repulsion is exerted. In fact, this entire bond will move down. This entire bond will move down, making the bond angle between two bonds smaller than 90 degrees. So when these bonds come down like this, it will not be a perfect square pyramidal shape that you observe. The square pyramidal shape is going to be slightly distorted due to these bonds coming up ever so slightly. So therefore, it won't be a perfect square pyramidal shape. So we say the shape of this molecule is distorted square pyramidal shape. So to observe the shape, let's remove this lone pair that is represented by this link, and you can see that it is a square pyramidal shape that you observe here. But keep in mind, the bottom four iodine fluorine bonds will move up a little. So therefore, there won't be a perfect square pyramidal shape. In fact, it is going to be a distorted square pyramidal shape. And the bond angle between each of these bonds are not going to be 90 degrees due to the bottom bonds coming closer to one another. It is going to have a bond angle that is smaller than 90 degrees. So you will not observe a 90-degree bond angle over here, and the final shape that you observe is normally referred to as distorted. It is normally referred to as distorted square pyramidal. It's not just square pyramidal, it is referred to as distorted square pyramidal. It is very important to keep that in mind. So when you have one lone pair in a octahedral electron pair geometry, when you have one lone pair, the resultant shape is going to be distorted square pyramidal. Distorted square pyramidal. Now, after observing that, we can move on to our next molecule. Now, students, we move on to ammonia. Ammonia ion has the following Lewis structure. Around the nitrogen atom, there usually is going to be 5 electrons. You can see around nitrogen we don't have 5. So because of that, we have a positive charge on nitrogen. When you normally draw the Lewis structure of the ammonium ion, the positive charge is going to be represented outside of the entire ion, as this charge belongs to the entire ion. So the ammonia ion has 4 bonds but no lone pairs. It doesn't have any lone pairs. So the overall number of electron pairs around the nitrogen central atom over here is going to be 4. and the total number of repulsive units around the nitrogen atom is also going to be 4. Do we see any lone pairs? No. So therefore, the number of lone pairs is going to be 0. And we know by now, when there aren't any lone pairs, the electron pair geometry and the shape of the molecule is going to be exactly the same. So we have only 4 repulsive units around the central atom. At that point, we have a tetrahedral electron pair geometry, and since we don't have any lone pairs, the tetrahedral electron pair geometry will produce the shape, tetrahedral shape, in the ammonium ion. So let's observe this shape, and to observe this shape, we will take this blue color ball to represent nitrogen, and we can connect hydrogens to nitrogen through these links. We can connect these hydrogens to the nitrogen atom through links that we have used so far. This white color balls represent hydrogen atoms. Now we are going to connect all 4 hydrogen bonds to nitrogen to form the ammonium ion, and the shape of the ammonium ion then can be very clearly observed after that. So this is going to be the shape of our ammonium ion, and this shape is a well-known shape to us. We observe this in methane as well. This shape is known as the tetrahedral shape, and the bond angle between 2 bonds is going to be 109.5 degrees. So students, after observing this shape, you have to keep in mind we are talking about iron here. It's not just the molecules that will have different shapes. Even ions, based on the number of electron pairs around the central atom of the ion, will have different shapes to it. So this is the first ion that we observed. The shape of this first ion we observed over here is going to be tetrahedral. Now let's move on to another ion. Now we are going to be observing another ion, sulfate ion. So if you take a look at the sulfate ion's Lewis structure, we can see there's sulfur atom in the middle, and there are 4 oxygen atoms connected to the sulfur atom. And around the sulfur atom, there are 6 bonds. 6 bonds will bring in 6 bond electrons. However, since there are 2 double bonds, the number of repulsive units here are not going to be the same as the number of electron pairs around the central atom. So the number of electron pairs around the central atom is going to be 6. However, the number of total repulsive units around the central atom is going to be 4. This is because there are 2 double bonds, and each double bond is going to be considered a single repulsive unit. We learned double bonds and triple bonds are considered as a single repulsive unit. And how many lone pairs do you see over here? No lone pairs. And the overall charge of the sulfate ion is -2. That is because these 2 oxygen atoms that we have over here each carry a negative charge due to an additional electron being present in them. So these 2 oxygen atoms that are connected to sulfur through a single bond will carry 1 negative charge each, which will bring 2 negative charges to the entire ion. So the sulfate ion has this Lewis structure, and we have observed the total number of electron pairs around the central atom, total number of repulsion repulsive units around the central atom and the number of lone pairs around the central atom. And we notice, since there are double bonds, the total number of repulsive units are not going to be equal to the total number of electron pairs around the central atom. Now let's demonstrate the shape of this ion using a yellow color ball that we have here. This has 6 holes. We are going to be using this particular this as the central atom. So we'll be using this particular ball to represent the sulfur atom, and we'll be connecting oxygen atoms with the use of these connectors. Now we can see that there are altogether 4 repulsive units around the sulfur atom. We know when there are only 4 repulsive units, the shape of that type of ion or molecule is going to be tetrahedral. So we see both the electron pair geometry and the shape of the ion is going to be tetrahedral. So we need to show this shape with the use of this yellow color ball and oxygen atoms that are usually denoted by these red color balls. So let's demonstrate the double bonds first. We will be connecting sulfur to oxygen through a single bond like this, but you know very well we have 2 oxygen atoms that are connected to sulfur through a double bond. So let's try to connect this oxygen atom to sulfur through a double bond. So when you are connecting, you can bend these links like I mentioned earlier in the beginning of this lesson. So we can see now this oxygen atom is connected to the sulfur atom through a double bond. We can see there are 2 links here indicating the double bond that exists between the oxygen atom and the sulfur atom. And there will be another double bond between oxygen and sulfur. Let's indicate that also like this. You can see that we bend these flexible linkers. Now we have produced 2 double bonded oxygen atoms to sulfur. So these 2 oxygen atoms are bonded to sulfur through a double bond. And then there are 2 oxygen atoms that are bonded to sulfur with just a single bond. Now students, this is going to be your shape of the SO4 2 minus ion. So after observing that this sulfate ion has a tetrahedral arrangement, we can move on to observe the bond angle. As you know, if there is a tetrahedral arrangement and if there aren't any lone pairs, the shape of the molecule also tends to be tetrahedral, and the bond angle between 2 bonds is going to be 109.5. Over here also, the bond angle between oxygen and sulfur bonds happen to be 109.5. So after observing the shape of sulfate ions, now we have the Lewis structure of the carbonate ion here. You can see we have a central carbon atom, and there is a double bonded oxygen to the carbon, and there are 2 oxygen atoms that are bonded through a single bond to the carbon. And these 2 oxygen atoms that are bonded to carbon with a single bond actually carry one negative charge each. So therefore, the entire ion possesses a 2 minus charge. So if you are focusing on the central atom, around the central atom we see 4 bonds, which means it brings about 4 bond electrons or 4 bond electron pairs around the central carbon atom. Although there are 4 bond electron pairs around carbon, the number of repulsive units around carbon happens to be just 3. This is because the double bond that we see over here is going to be considered a single repulsive unit. So therefore, the number of repulsive units tend to be 3. The total number of electron pairs around the carbon atom is 4, but the total number of repulsive units around the carbon atom happens to be 3. And we don't see any lone pairs, so therefore, the number of lone pairs would be 0. And since there aren't any lone pairs, based on the number of repulsive units we see here, we can get to the shape of the molecule. The shape of the molecule happens to be trigonal planar, as there are 3 repulsive units. The shape of the molecule is trigonal planar. And electron pair geometry and shape of the molecule happens to be the same. Electron pair geometry is also trigonal planar, and shape of the molecule is also trigonal planar. Now, we'll be taking these black color balls to represent the carbon atom. There are 4 holes in them. And we'll be using these linkers to connect the oxygen atoms to the black color carbon atom that we have over here. So we'll first represent the double bond by connecting an oxygen atom to the central carbon atom with the use of 2 bonds. We can see over here the oxygen atom is connected to the carbon atom through 2 bonds. And apart from that, we can connect 2 other links and 2 other oxygen atoms to complete this carbonate ion and form a trigonal planar carbonate ion structure. So you can see, we say this is a trigonal planar molecule. We say that this is a trigonal planar ion. This is because if you observe very closely, you can see all of these atoms in this ion, all of these atoms are going to be found on the same plane. All of these 4 atoms in the carbonate ion are going to be found on the same plane. Although we can see these double bonds according to the way that we have constructed this model, we can say that they are protruding out, but still the atoms are in the same plane. All of these 4 atoms are going to be in the same plane. If I keep the molecule like this, so if I keep the ion, carbonate ion model like this, you can see all of these atoms are going to be in the same plane, indicating that this is a planar ion. So the shape of this ion is going to be trigonal planar. And the bond angle between each of these bonds is going to be 120 degrees. Now, after observing this ion, we are now going to be moving on to the nitrate ion. Now, we are going to observe another polyatomic ion that has the same shape as carbonate ions does. And that ion is the nitrate ion. You can see the Lewis structure of the nitrate ion. You can see the central nitrogen atom, and if you observe this Lewis structure around the nitrogen atom, there are only 4 electrons of its own, meaning nitrogen atom is missing an electron, so therefore nitrogen is going to be positively charged in this Lewis structure. And the 2 adjacent oxygen atoms that are bonded through a single bond are actually going to be carrying 1 negative charge each. This is because oxygen has 1 additional electron in them. So therefore, oxygen atom carries 1 additional charge each. So each oxygen atom has 1 negative charge, and there's 1 positive charge on nitrogen. So the overall charge of this ion is 1 minus. 2 negative charges and 1 positive charge together will have an overall charge of 1 minus. Now, let's observe the number of electrons around nitrogen. You can see that there are 4 bond electron pairs around nitrogen. So the total number of electron pairs around nitrogen is going to be 4. But there is 1 double bond. As we know, a double bond or a triple bond is going to be considered a single repulsive unit. So the number of total repulsive units around the nitrogen atom happens to be 3. 1, 2, and 3. So the total number of repulsive units around the nitrogen atom is 3. We don't have any lone pairs. So the electron pair geometry, when there are only 3 repulsive units, is going to be trigonal planar. And the shape of the molecule is going to be trigonal planar as well, since we don't have any lone pairs here. To demonstrate the shape of the nitrate ion, we'll be using these blue color balls, and we'll be using these linkers to connect the blue color balls to these red color balls that will be representing our oxygen atoms. We will connect these bonds to the oxygen atom, and then we can bend these links. Now, since we have connected the oxygen atom to the nitrogen atom we have over here, you can see the double bond, and through single bonds we will be connecting another 2 oxygen atoms to the nitrogen atom. And we can now very clearly see the trigonal planar shape. You can see that when we are rotating this structure, you are going to be able to see how all of these 4 atoms are going to align in a single plane. You can see right now all of these 4 atoms are aligning in a single plane, indicating that all 4 of these atoms are in the same plane. That's why we use the phrase trigonal planar to explain the shape of this ion. So a similar shape was observed in carbonate ions as well. They also have the trigonal planar shape that we observe here in the nitrate ions. So nitrate ions and carbonate ions both have trigonal planar shape, and apart from that, the bond angle between each of these bonds are going to be 120 degrees. Now let's move on to the next ion. Now students, let's take a look at the oxygen molecule. We have the Lewis structure of the oxygen molecule here. We can see 2 oxygen atoms connected to one another through a double bond, and each oxygen atom contains 2 lone pairs. So altogether, around oxygen atoms, you have 4 electron pairs. 2 of them are bond electron pairs, and 2 of them are lone pairs. So all around the oxygen atom, we have 4 electron pairs. So around the oxygen atom, there are a total of 4 electron pairs. And the number of repulsive units around one oxygen atom happens to be 3. So when there are 3 repulsive units, the electron pair geometry is going to be trigonal planar. However, 2 of these repulsive units are going to be lone pairs. So at this point, the shape of the molecule is going to be linear. So the shape of the molecule is linear. So let's observe this with the use of these red color balls we have in our molecular modeling kit. So these red color balls are used to represent oxygen atoms, and these links will be used to represent bonds. So we are going to connect these bonds to each of these oxygen atoms like so, and then the second bond is going to be connected to each of the atoms by bending these links. They can form the oxygen molecule. So only 2 double bonds can be seen here connecting the 2 oxygen atoms, because oxygen molecule is made out of 2 double bonds connecting the 2 oxygen atoms. And you do not have any lone pairs appearing in the shape of the molecules, as I mentioned earlier as well. So the shape of the oxygen molecule is going to be linear. Shape of the oxygen molecule is going to be linear. Electron pair geometry around one oxygen atom of this oxygen molecule is trigonal planar, and the shape of the oxygen molecule happens to be linear. Now let's move on to observing the shape of the nitrogen molecule. Now we have the Lewis structure of the nitrogen molecule represented here. You can see the 2 nitrogen atoms are connected to one another with a triple bond. So each of these bonds carry 1 bonding electron pair. So around one nitrogen atom, there are going to be 3 bond electron pairs. Apart from that, there's going to be a lone pair as well. So around a single nitrogen atom, we can find 4 electron pairs. But as you know, the total number of repulsive units are going to be just 2, because this triple bond or any double bond or a triple bond are always going to be considered a single repulsive unit. So this triple bond will act as a single repulsive unit, and this lone pair will be another repulsive unit. So therefore, the total number of VSEPR repulsive units are going to be 2 when it comes to our nitrogen molecule. And one of those repulsive units happens to be a lone pair. In this case, since there are only 2 repulsive units, the electron pair geometry around that nitrogen atom is going to be linear, and one of them is a lone pair. So the final shape of the molecule also happens to be linear. Let's observe the shape of the nitrogen molecule. To represent nitrogen, we will be using these black color balls. We will need 2 black color balls to represent the nitrogen atoms in the nitrogen molecule, and we'll be connecting them with these links to one another. So let's connect them. So we have now connected these two nitrogen atoms with one bond, but as you know, there are 3 bonds in nitrogen. So the second bond goes here, and we'll have to bend these links to connect these 2 bonds like so. Now we have connected the 2 nitrogen atoms with 2 bonds. Finally, we have to include the third bond, which is going to be connected like this, forming a nitrogen molecule that has 3 bonds in it. You can see this is the nitrogen molecules 3D model that we constructed. So it's very clear that it's a linear molecule. When there are only 2 atoms, you will observe the shape of those types of molecules happens to be linear. So this nitrogen molecule also happens to be linear. Now, after observing the shape of our nitrogen molecule, we are going to now move on to observe the shape of a hydrogen molecule. Now, we are going to observe the shape of the hydrogen molecule. Hydrogen molecule has this Lewis structure. You can see between the 2 hydrogen atoms, there is a shared pair of electrons. So this shared pair of electrons, this is not a lone pair, students, don't get mistaken. Whatever the electrons that you find between 2 atoms, like this, is a shared pair of electrons or a bond electron pair. And hydrogen doesn't have any other electrons around it. So therefore, this is only going to contain, or a hydrogen atom found in the hydrogen molecule is only going to have 1 bond electron pair around it. There won't be any lone pairs around the hydrogen atom. So the total number of electron pairs around the hydrogen atom is going to be 1, and the total number of repulsive units around the central hydrogen atom is also going to be 1, because there aren't any other lone pairs or anything like that. So therefore, the total number of repulsive units are also going to be just this bond electron pair, and there aren't any lone pairs, as I mentioned earlier. So the electron pair geometry and the shape of the hydrogen molecule happens to be linear. Hydrogen atoms are represented with white color balls, and we can very easily show the shape of hydrogen molecule by connecting one hydrogen atom to another hydrogen atom through a link like this, showing that the hydrogen molecule is linear. What we have formed here is a hydrogen molecule, and it is a linear molecule. With that, students, we can conclude this part of our experiment. We are going to be moving on to a small summary to give you an idea about the different shapes that we can obtain through a single type of electron pair geometry by changing the number of lone pairs in it. So let's move on to that part now. Students, in a previous summary, we observed when there are only 4 repulsive units, the electron pair geometry of that type of molecules are going to be tetrahedral. And we observe the shapes of the molecules when this electron pair geometry of tetrahedral has 1 lone pair and when it has 2 lone pairs. And even when it has 3 lone pairs, we observed what the shapes of the molecules are going to be. Now we have a structure here that is known as the octahedral structure. If you take a look at this structure, you can see we have altogether 5 bond electron pairs. So therefore, the electron pair geometry of this particular molecule, trigonal bipyramidal. This is an example. We do not specifically study just the molecule and its name. We are trying to show when it comes to the trigonal bipyramidal electron pair geometry, how the shapes of the molecules change when we keep on replacing each of these bond electron pairs with a lone pair. So over here, all of these electron pairs are bond electron pairs. We don't have any lone pairs here. And there are a total of 5 repulsive units. So the shape of this molecule is going to be trigonal bipyramidal, and the electron pair geometry also is trigonal bipyramidal. If you remove one atom and replace it with a lone pair, what will be the shape? We observed such a molecule in our examples. Sulfur tetrafluoride, we observed, had this seesaw shape where one lone pair was present and the entire electron pair geometry was trigonal bipyramidal, but the shape of the molecule was described as distorted seesaw shape. The seesaw shape is basically because this appears like a seesaw. But since there is a lone pair here, these 2 bonds will be bent a little bit, producing a distorted seesaw appearance. So when you replace one bond pair of electrons in the trigonal bipyramidal electron pair geometry, when you have one lone pair, the shape that is going to be resultant is distorted seesaw. If you have 2 lone pairs, if I remove this atom as well, we can see that there are 2 lone pairs now. At that point, the shape of that type of molecules are going to be distorted T-shape. There is a nice T-shape here, but don't forget there are 2 lone pairs. So therefore, it's going to have this distorted T-shape. After that, if you continue to remove one more atom and have 3 lone pairs, the shape of the molecule happens to be linear. You can very clearly see the shape of the molecule happens to be linear, and the 3 lone pairs are going to be present with 120 degree separation among them, and the bond pairs are going to be present with 180 degree angle between them. So when you are starting with trigonal bipyramidal electron pair geometry, if all of the repulsive units are bond electron pairs, you will observe the trigonal bipyramidal shape. If you have trigonal bipyramidal electron pair geometry and one repulsive unit is a lone pair, you observe the distorted seesaw shape. If you have the trigonal bipyramidal electron pair geometry and you have 2 lone pairs, you observe the distorted T-shape. And finally, if you have the trigonal bipyramidal electron pair geometry and you have 3 lone pairs in that molecule, you will observe a linear shape. So that is how the trigonal bipyramidal electron pair geometry will produce different shapes of different molecules based on the number of lone pairs of electrons found in such a geometry. Now, let's move on to the octahedral electron pair geometry. Now, we are going to be looking at what type of electron pair geometry can be seen when a molecule or ion has exactly 6 repulsive units around the central atom. So when you have 6 repulsive units around a central atom, and if all of these repulsive units happen to be bond electron pairs, the shape is going to be tetrahedral. One good example will be sulfur hexafluoride. So you can see we observed this shape earlier. Since there aren't any lone pairs, the electron pair geometry is going to be octahedral, and the shape of the molecule is also going to be octahedral. Now, what happens if you replace one of the bond electron pairs with a lone pair? Now, when I remove this atom, that indicates that this is a lone pair, and the rest of it is going to be bond electron pairs. So at this point, what you see here is a square pyramidal shape. However, students, we learned due to the lone pair present beneath this square pyramidal shape, these bonds will bend somewhat upwards, all 4 of them, not bend, they will move upwards, and due to that, the bond angle between each of these bonds will reduce. They won't any longer be 90 degrees. So when they move upwards a little bit, you will not have a perfect square pyramidal shape. Instead, you will have a distorted square pyramidal shape. So that is when you have the octahedral electron pair geometry, but one repulsive unit is a lone pair, and the other 5 repulsive units are bond electron pairs. What happens if you have 2 lone pairs while retaining the number of repulsive units at 6? So in this case, you have 2 lone pairs and 4 bond electron pairs. The total number of repulsive units are 6. So the electron pair geometry is octahedral, but the shape is known as square planar. We can see all of these atoms are in the same plane. So we call this arrangement the square planar arrangement. All of these atoms are in the same plane. So that is when you have 2 lone pairs and 4 bond electron pairs. We can further remove another atom and observe what happens when a molecule or ion is present with 3 lone pairs and 3 bond electron pairs. You observe a shape that is known as the distorted T shape. Due to the lone pairs that are present, these bonds will move a bit down. They won't bend like this. Instead, they will move closer to the other bond. So therefore, the bond angle between them will decrease. So this is not a straight T shape that you observe. Instead, it's slightly distorted. So therefore, we call it the distorted T shape. If another atom is removed and you have 4 lone pairs and only 2 bond pairs of electrons, the shape would be bent. And if you take it a step further, you can even see the formation of a linear molecule. So students, you have to understand how the shapes of molecules will change when you have a similar electron pair geometry but different number of lone pairs in different molecules. So if you have the same electron pair geometry but different number of lone pairs, you now observed how the shape of those different molecules will change. I hope you have obtained a good understanding about the shapes of molecules and ions through this practical. Let's move on to the next part, where we will be talking about some additional theory parts and questions that are revolving around this practical.